interesting because you could potentially have applications to like power systems within a satellite, and that's fun too. That requires a little bit of different kind of tether technology.
This is for thrust, for orbital maintenance?
That's kind of what I'm more interested in, and that's a little bit about what I'll be talking about today.
So how long are these tethers?
That's an excellent question. So I'm going to have a video in my very next slide that will show a mission called SEDS-2. One of the reasons why I'm kind of an advocate about this technology is that I really like it. It's interesting because it's very different than a rocket, which we're all familiar with rockets. You know, they use chemical propellant. They burn up and they will use up that propellant over a given amount of time, and that will be kind of that. This guy uses something that's freely available, and that's free-floating charged particles, ions, that are just kind of out there in the plasma. And this particular tether experiment was flown in 1994. This gentleman, Joe Carroll, is a lifelong contractor with Naval Research Lab and NIAC, which is like a double acronym. It's the NASA Advanced Concepts Program. Joe Carroll's a great guy. He used to be a high school math teacher and is just amazingly bright, and I'm very proud to call him something of a mentor. He's just somebody I could learn a lot from, and I've been very blessed, I think, to kind of meet him. So these two guys are both 20 kilometers long. They were flying, as you can see, by the very, very advanced mid-90s home video technology that we're seeing here on April 5th and 6th, 1994. SEDS is a small expendable deployer, so basically it went up as a secondary payload, it unraveled, and without any trouble with the deployers, which deployers have been in trouble in the past, and we'll talk about that in a little bit, this guy was able to unravel to about 20 clicks. And what's fun is that you can see it. If we had a tether of this size, we could all step outside, even with the sky glow of Los Angeles, and we could have a look. So if you'd like, which I think maybe folks would, I'll play the short video, one video, from the SEDS-2 mission. And I'm sorry, Adobe, we'll come back to you later. And it'll kind of give you a sense of exactly what we're talking about here.
Is this the one that snapped, or it had like such a high energy load that it actually...
Nope, that was STS-75, and we're going to get to that eventually. So this will just kind of give you a sense of how these guys move, because it's a little weird. So this is a 20-kilometer tether. It tends to want to grab at the electrons, and the electrons tend to kind of hang out around the field lines, so it tends to kind of want to snake a little bit, or wrap itself around things. And this guy, I think, was up for about 2 or 3 weeks, and eventually came back down. I'm going to say this probably 5 more times at least, but these are all science missions. In my opinion, we could really benefit from a little bit of technological maturation and development that could kind of bring this kind of technology into a more applicable use with some interesting spacecraft designs. We'll get into that in a second.
When it came down, could it be controlled? Or it just falls?
As a point of fact, that particular one, SEDS-2, I don't think could be. But there are some more advanced concepts. We're going to talk about EDDI in a second. EDDI is a more advanced electrodynamic tether concept that is going to be potentially used, should they get funding, for debris removal. I'm going to kind of draw the parallel, bring these two threads together as far as how tethers and debris kind of make sense in just a second. But yeah, that's you know, your basic tether.
So these are like proof of concept experiments?
Not even really. So they want to know, okay, for example, I brought a paper, Juan San Martin is kind of a ranking authority on tethers and has published quite a bit. It's big with ESA and has done a little bit of work for NASA as well. All they want to do is measure voltage. So they want to know how much tether, you know, real estate buys you how much voltage. And on his paper, which I brought, if anybody's interested, it was published in '93, basically says that for about every kilometer that you've got of tether, you're good for about 200 volts. So it's not bad. It's great because it's kind of free. It's not really free. You have to, you know, expend energy to get things up there, but it's kind of free. Free in the sense of, this is the analogy I like to use. So if this were 1850, and I were to say that underneath the ground, where we all stand right now, is this vast source of energy, right? All you got to do is dig it up, get to it, put it in barrels, send it off, and find somewhere to sell it. If I told you that, just for 1850, you'd say, that sounds crazy. By the turn of the next century, we have a fair number of oil magnates who are doing exactly that, and had found a very unique way to put those kinds of resources to use. I am that guy in that 1850 scenario, and I'm desperately saying, along with a few other people who are advocates of this kind of technology, that this kind of tech is great because it uses something that's already there, and that's ionized particles.
So when you say 200 volts per kilometer, what kind of load? I mean, you have to have amps. With,
sure.
Understand power.
That's still being worked out.
A
few of these things have burned up. And in fact, they used what now is called braided spectre tether, which is like bare copper wire and an interesting kind of I don't even know what to call it. It's like a plastic, basically.
Okay.
They've melted, they've snapped, they've burned.
So they're not placing loads on these?
Not just yet.
Okay.
They've all been science experiments. One of my final points I'm going to close with is about some interesting ideas as far as how we can do a little more on-the-ground testing to mature that technology. Basically, if we all had access to LEO, we could grab a spool of copper wire and basically do kind of what NASA has done quite a few times. So I'd like to talk about STS-75. STS-75 was unique in that it went up in '96. Dr. Franklin Chang Diaz, who is by far my favorite astronaut of all time, was in charge of this particular mission, or was in charge of this particular experiment. STS-75 was interesting in a couple of ways. There were some rumors floating around that they were doing experiments on sexual positions in microgravity, which is entirely untrue. Right? Keeps it interesting, but not necessarily. Sorry, again.
Did it help get funding?
Actually, for that sort of thing, that's the sort of thing that'll help you lose astronaut status, as we've seen recently. But also that there was potentially a UFO sighting, which actually ended up just being orbital debris out of focus, of course, depending on who you ask. What is actually 100% true about this particular mission is that it was almost entirely devoted to tether technology. There were like 12 different tether experiments that were on board, associated with a couple of pieces of hardware. Also, for those of you around here who are programmers, the first time Linux was ever used in flight on the space shuttle. Basically what happened was that this tether went up. It was a 20-foot tether, very, very similar to SEDS-2. They deployed it to about 19.1 kilometers, and it broke. And it was visible, kind of like we just saw SEDS-2 was visible for quite some time. And eventually, it did come down. And they did not get the results that they could have had it, function in the capacity they would have liked. But it was JAXA is most recently kind of keeping this whole thing alive. They flew a tether mission in 2010, and nothing slated as far as like the initial future is concerned from the government sector. But there are some interesting commercial ideas that are floating around. We'll get to those too.
What's Spasimir?
Oh, that's a great question. So Franklin Chang Diaz is like this legend now. He's flown like 7 times. He is very, very interested in a particular kind of propulsion called Spasimir. It's a variable specific impulse propulsion that utilizes plasma. He has basically a mock-up of it that sits in a lab. He's got, I think, a space in Texas that he works out of. And supposedly, and I have no official word on this just now, but they're going to send it up to ISS to do like a potential reboost maneuver utilizing Spasimir.
Really?
Obama gave a shout out to Franklin Chang Diaz and they raised some eyebrows because, like a lot of tech in development, it's really not ready. He's developed, I think, every single component associated with it, and it's spent like 30 years on it. It's like a big pet project for him. Like a lot of folks who want to see, traveling into deep space or at least exploring our solar system being a possibility within our lifetime, I keep like a little ray of hope alive for Dr. Franklin Chang Diaz because I hope he's successful.
Is there something you can describe about Spasimir that is, various variable specific impulse? I mean, what makes it different from other types of plasma?
I don't know enough about the science and tech to argue that or make any good points about it. All I can say is that it utilizes plasma, a plasma reaction that basically, like any kind of specific impulse, keeps a charge going for a particular amount of time, or keeps thrust going for a particular amount of time. But his exact tech process, I would point you to the web. Ad Astra Rocket is his company, and he's a public guy. He wants people to know about what they're doing, so I'm sure there's more stuff floating around out there. Okay, so let's get to applications. As I said before, I'm interested in, and continue to be interested in, orbital debris. One particular application which I really like for tethers is end-of-life satellite disposal. I got introduced to this and with a colleague wrote an SBIR solicitation proposal proposing that this sort of technology be utilized to navigate satellites when they're out of propellant. We didn't get it, unfortunately. The Air Force doesn't like tethers because they see them as a liability. So if you have this platform that's 2 meters by 3 meters, whatever, and then suddenly now it's 20 kilometers long, basically you have a 20-kilometer long spacecraft. So to them it's a liability. I remain committed to the technology, and despite the fact that it didn't work in that particular case, we have some other ideas that I kind of have cooking that I see that could still work with tethers. But unfortunately, the Air Force thinks it's a bit of a liability. But where I think it could be really useful is if you see here the red and the green business on your right, is the Iridium Cosmos incident. If anybody's familiar with that, in 2009 over the North Pole, an old Cosmos Soviet-era satellite collided with one of the active Iridium constellations. Iridium, if anybody has a journalist friend, knows that basically it's a cell phone that works anywhere on the planet, which is kind of cool. They have a nice constellation of satellites going, one that's in a bad way now because it collided with Cosmos over the North Pole, scattering debris everywhere. It's a great example of how, had you had preventative measures on your platform before going up, you could have navigated out of the way or done a controlled burn and basically ended a potential threat by just this, floating refrigerator, which is kind of what Cosmos was at the time that it hit Iridium. And now that debris field is propagated all over the globe, and it's issues for a lot of folks. The top artist concept here, I strongly dislike because if you look at it, it kind of has nose, wings, and a tail, and it kind of looks like a plane. The situation with the technology is that it doesn't require the same kind of aerodynamics that fixed-wing aircraft do. So having that kind of description doesn't help NASA and whoever that artist was who came up with that concept. I hope he was fired or at least reassigned elsewhere. Just doesn't effectively communicate kind of what this stuff can do. It's not a plane. And in the bottom diagram is a potential mock-up for a climbing robot, and that's something that I also see as a potential application for electrodynamic tethers. The issue right now isn't keeping something up in a particular place in space, it's making something strong enough to remain taut, either without giving out or without snapping, to keep potential space elevator, like the rope for it going. If anybody knows about the photovoltaic robot that Laser Motive has, that won that Centennial Challenge. Basically, they shine a laser up at photovoltaic cells on the climbing robot, and they follow the laser with the robot all the way up, and it climbs a particular rope. So the tech is there. Laser Motive won a $900,000 prize. I think that was the level 2 of it. Level 1 hasn't yet been satisfied. Such and such a feat over such and such amount of time. But the tech is there, and so the idea that science fiction writers have kind of conceptualized for years. That we could potentially have access to space via an elevator, it's very real. And all we kind of need are, reinforced carbon nanotubes to get us all the way up to, I think, potentially geosynchronous orbit, which is like 22,000 miles up. I think the longest bit of carbon nanotube that's ever been manufactured is like 18 centimeters. So there's a little ways to go. Indeed. It's another fun tether search. So anybody, pardon me. And anybody familiar with the documentary film Orphans of Apollo? Okay, just the gist. So a bunch of guys, this is like when New Space, the idea of commercial space endeavors was brand spanking new. This guy Walt Anderson, who made a bunch of money in telecom, decided that, hey, I love space and I've got a ton of money and I would love to go up to space. And this is like before Dennis Tito went up and paid his $20 million to go. This is before the NSYNC guy was going to go and then didn't go. So this is all very new. It was about 10 years ago. So the Russians decided they had built Mir, and they loved Mir. Mir was great. It was modular in that, just like the ISS, they could keep building things for it, shipping them up to space and adding them on. So it's kind of like Legos. You could just kind of keep expanding it and grow and grow. And this is the final kind of concept of what Mir was. And it's beautiful and a little bit archaic in places. The first module went up in 1986. The last bits of it went up in late 2000. So some of it was brand new, some of it was very old. These guys, Walt Anderson, and if anybody knows who Rick Tomlinson is, they're just characters. Walt Anderson is currently in federal prison for not paying taxes. Something avoided $600 million or something to go to taxes. Bad stuff. And so he'll be joining us in the free world, I think, sometime next year, after I think spending about 8 or 9 years in prison. Rick Tomlinson is still active in New Space and actually spoke at Space Up and has been at another few events. He's a friendly guy and very charismatic and kind of what New Space needs. These guys got together back in 2001 and they contacted the Russians. They said, hey, you have Mir and you're going to just deorbit it, you're going to burn it. We want it. We'll develop a lease and we'll take it off your hands. What do you say? And if anybody remembers that time of the world, oil prices were very low and the Russian economy is basically almost entirely dependent on natural resources for their stream of income. So, let's go through it again. I'm sorry. So long story short, for $20 million, they developed an idea to take control of the mirror. And their idea was, we'll give it to you in 3 parts, as long as you can get our guys up there and help refurbish this thing, because it had been left empty for a little while, which is always dicey. You don't want to have to go back into something that's been left abandoned in space. It could be no air, it could be, I don't know, it could be all the stuff horror movies are made of. But long story short, they cut a deal, and the Russians liked it because Russians have this kind of rocky history with NASA in that if we want to book a flight to go up on a Russian vehicle, we will do it, but we'll make, you know, Roscosmos, the Russian space agency, sound like 400 documents before doing it. So they have all this bureaucratic bullshit they have to go through. Russia doesn't like that. And so if I'm Dennis Tito, this billionaire who just wants to pay $20 million to go up, the price for Dennis Tito is $20 million. But if I'm a US astronaut, and along with me going up are 400 pages of paperwork, the price for my ticket is $65 million. The Russians. So basically, Tomlinson, Walt Anderson, and the rest of his cadre, I really insist, Orphans of Apollo is like 45 minutes long, it's a brilliant documentary. They had a lease that said, basically, we have this property that you own, the Russians own, and we want to lease it for X amount of time, for X amount of dollars. And it came in with like a 1-page deal. And the Russians said, oh, you know, let's do it. You know, they have a couple of drinks, they celebrate, and the first installment of $7 million gets handed over. The problem was that the US doesn't like it when stuff like that happens. They want to be included. And specifically, an electrodynamic tender is going to be exported over to Russia to go up, to take it up to Mir, because its orbital slot was degrading, and they were eventually going to come down sooner than they would have anticipated, sooner than they would have liked, especially if you're just, you know, buying or leasing this piece of property in space. So they wanted to export the tether, and the tether was basically going to go up. It was going to be a space-facing tether. It was going to grab the plasma, and it was going to slowly reboost Mir up to a safer place. Buy them some time, they could clean it up, maybe turn it into a hotel, whatever. It was their interest. But the State Department has to approve anything that goes into space because in their eyes, anything that goes into space is a potential weapon. So if I have something that can reboost Mir, then I could potentially also use that to deboost Mir in a strategic way that might fall, say, on 1600 Pennsylvania Avenue, heaven forbid. That's the way they look at it. And they didn't like the idea of having to sign off on something like that. And it became a little bit of a rocky situation. The former head of NASA at the time publicly derided this particular idea. They were trying to make a space for the ISS. That was their new big pet project. All kinds of member nations that were involved in that one going up, and they wanted Mir to go away, and they wanted the ISS to go up. So both NASA and the State Department had a vested interest in this not working out. And as we can see on the picture on the right, that's what happened to Mir. So needless to say, all the money changed hands, or a significant portion of the money changed hands. They didn't get to do what they wanted to do. They had one flight set up to go to Mir, and they kind of fixed it up a little bit. And I encourage you to watch Orphans of Apollo because I could talk for an hour on that movie alone. And it's a fun film. So, getting back to the orbital debris problem. So, as we've seen in recent news, things fall. We had a UARS re-entry, which is the Upper Atmosphere Research Project from 1981 that came down. That burned up. It landed in the Pacific Ocean. Recently, ROSAT, which is a German space telescope, re-entered and landed in the Bay of Bengal, the coast of India. So, safe places to land, right? The Earth is 2/3 water, 67% chance that anything that falls doesn't land on the Earth, or doesn't land on land. So that's a nice thing. But as we can see, everything that falls doesn't necessarily either burn up or fortuitously land in the ocean. We see some gentlemen here inspecting this fallen titanium rocket casing that landed in Saudi Arabia. Titanium tends not to burn. The 3 fellows on the left of that photo are very interested in what's inside. Nothing's inside, everything else would burn up. But things fall, and the orbital debris problem isn't going away anytime soon. There are thousands of tons of debris, especially in these kind of like messy inclinations. The Russians are kind of interesting in that they're very methodical. So like, okay, I've got a Russian rocket, and it's called a Zenit, and I've been sending my Zenit upper stages to the same spot every single time because they just like to do what works. And so there's like bad inclinations, like 101 to 103, where you have all of these spent rocket bodies all in the same orbital inclination, all in the same mix, and it's really kind of messy. And big debris creates smaller debris. So something like 10,000 pieces of debris are trapped, which are 10 centimeters and above. Again, the American government is interested in what could be potentially weapons, so they feel that nothing smaller than 10 centimeters could be a weapon. So they don't really keep an eye on that sort of thing. But big things do come down, and big things do make smaller things. So that brings us to Eddie. As I mentioned before, tethers are interesting in that they're kind of versatile. And Jerome Pearson, who's a colleague of Joe Carroll's, and a few other guys, Eugene Levin, a former Russian, now a naturalized American, are working on Eddie. Eddie's great, so here's the idea. You send Eddie up, you unspool it. It's kind of like a ribbon or a snake in that you can use it once and you can keep using it. So you send your Eddie up, it wriggles up to your spent rocket body, and you bring it back down and you navigate your rocket body to a convenient location. What they envision doing, and this is super ambitious, and I love Joe Carroll, I haven't yet met Jerome Pearson, but I like the way he thinks. They want to do like a $500 million on-orbit recycling facility. Very ambitious. I love the spirit. Jerome Pearson is 74 years old. I don't know that that will happen within his lifetime. I do wish them the best, though, because I think it's a novel use of the technology, and that's the kind of thinking that will help move this sort of thing forward.
Recycling in orbit.
You bet. Why bring it down if you spent so much money, so many resources to put it up, is the idea. So, the future of tether technology is largely dependent on access. And access right now is a little bit of a sticky wicket. Some folks may hear from NASA types that they're a little bit upset that we don't have a LEO access capability right now. I think we will, and it's this gentleman right here standing with the beautiful rocket that will give it to us. SpaceX is just down the road. It's in Hawthorne, off of Crenshaw Boulevard. Elon talks about taking humanity multiplanetary, bringing us this multiplanetary species in the future. That's a start. That's a really good start. And like I said, it's down the road from here. Very inspiring time to kind of be alive. In fact, in the next 5 years, I envision access, 5 to 10 years, access changing kind of significantly. There's another Centennial Challenge prize that's up right now. It's called the NanoSat Launch Prize. Any of you, should you have a rocket background, would be interested to participate. Basically, NASA is dangling in $2 million. If you can send up a 10-centimeter cubed, 1 kilo weight CubeSat up 2 times in a week, you satisfy the prize. I know a couple of interesting individuals, Paul Breed in particular. I could see him doing it. And whoever has that access now has access to LEO.
How far up does it have to go?
That's a good question. I would say probably somewhere on the order of like 200 clicks, 200 kilometers. But you would have to go to the Centennial Challenge website for all the specifications.
Right.
And
Okay.
I'm sure Larry Cooper runs the prize. He would love to chat with you and see about that. So we'll see how it goes. This is Jerome Pearson again. He has some interesting ideas. Again, these are what he calls his advanced spacecraft, Star Tech. This is his company, Star Technologies. Doesn't really look like anything we've seen before with respect to how you can navigate in LEO. You're not going to take this too much higher than 600 clicks without having to kind of reboost or at least drop back down a little bit and kind of get a little bit more, collect a little bit more electrons for your delta V. But we're not talking about rockets, we're not talking about planes, we're talking about utilizing available plasma, utilizing available electrons in the plasma. And that's what he sees as being the future, and quite frankly, even though those wouldn't be my particular designs, I do like the way he thinks. And I think that tether technology has very, very interesting potential applications not that far down the road. My big call, which is kind of what I'm after right now, is further iterative development of this tech. We never have had a point where we could recreate orbital velocity on the ground with an electron charging gun, with vacuum chamber, the whole bit, to where I can tell you right now, like maybe here in this space, it's a nice big space, what it would be like in LEO, in an electron-rich environment. And that's something that I think all of us could benefit from, or at least folks in the tether world could benefit from. This little roadmap here kind of shows where tethers have started and where NASA would like them to go. I see great potential for commercial application here. In fact, as access is open in the next decade or so, there are interesting ideas that could be exploited, and this tech kind of really needs to be developed. So, in closing, we'll see what happens with Eddie. That's the biggest kind of, on the horizon at least, the biggest potentiality of like a large-scale deployment of tether technology. But I'm sure there will be others. There are some interesting names in the mix and some very bright people who are engaged in this tech. So, if there are any questions, I am happy to entertain. Gary?
Do the tethers create any kind of drag going through the
Sure.
atmosphere? Yeah.
Yeah, you don't, the line that I've heard is you don't get something for nothing. Because, and here's another thing too, you couldn't like, I couldn't steer the space shuttle. Like if I had the space shuttle up and I wanted to, you know, really buy some serious delta V, it couldn't be done. You can augment drag and you can reboost your orbit, but you can't, you know, I couldn't like fly up to geosync. It's not that much. But if you were small enough, maybe you could. So what?